We're going to review now SN1 and E1 reactions, and we review them together because they're always in competition with each other. So it's almost pointless to review them in separate. When you find good reaction conditions for an SN1, you have also found good reaction conditions for an E1 and vice versa. So how do these reactions occur? We start with the proper electrophilic substrate. This one's going to be a good one because it's tertiary, and we'll talk more about that in just a moment. But look at the carbon that bears the leaving group. It is simultaneously bound to 3 carbons. That makes it tertiary. We've got a good leaving group, we've got a polar solvent, we've got everything we need here for a good SN1 reaction. The reaction begins with spontaneous ionization of the leaving group in order to produce a carbocation. Now this is going to be a slow step because carbocations are high energy and difficult to form. And because it's a slow step, it's not going to be competitive, at least in terms of rates, with reactions like SN2s or E2s. If there was a good SN2 or a good E2 reaction that were possible under these reaction conditions, it would flat out dominate because this is such a slow step. But there's not good. These are not good E2 or SN2 reaction conditions. The substrate is wrong for an SN2. We don't have a strong nucleophile, we don't have a strong base, we don't have all the things we require for those SN2 and or E2 reactions to occur. So this slow SN1 and E1 process will in fact be competitive. So the first step, whether it's SN1 or E1, is going to be spontaneous ionization to form this carbocation. Now, it's at this point that these two reaction pathways diverge. We've generated this carbocation and this anion in this sea of polar solvent, and they will dissociate from one another in the polar solvent, probably rapidly. And once they dissociate from each other, they can no longer react with each other. So what's going to happen? Well, in the SN1 pathway, our carbocation is going to react with one of those solvent molecules, water. It is not a good nucleophile. It's a weak nucleophile, but we have an excellent electrophile, a super electrophile in this carbocation. And so our water, even as a weak nucleophile, is acceptable here in an SN1. It will attack the super electrophilic carbocation, and the result is that we generate an oxonium ion. So when one of these lone pairs attacks, that creates the 2 electrons, or those are the 2 electrons needed for this carbon-oxygen bond. The result is this oxonium ion. Notice the oxygen only has 1 lone pair left. That's that lone pair right there. Still has its 2 bonds to hydrogen. If you count up the total number of electrons that this oxygen atom owns, it's only 5 now. Should have 6 to be neutral. So it's got a positive charge. It's an oxonium ion. We can finish off the SN1 pathway by simply bringing in another molecule of water and pulling off one of these acidic protons. That gives us our organic product, which is tertiary butanol plus H3O+. So this is our SN1, organic SN1 product, tertiary butanol. Now what if this was an E1 pathway? What would happen? We would, once again, start to consider this process with the carbocation, this tertiary butyl cation. The only difference is, in an E1 process, the water, rather than behaving as a weak nucleophile, is going to behave as a weak acid. A weak base. Our acid is actually this carbocation. If you look at the carbon that bears the positive charge in the carbocation, all of these carbons are 1 carbon away, they're alpha. And they all have hydrogens on them. I'm going to draw a couple of these hydrogen atoms in right here on this particular methyl group. All that will happen is that our water will behave as a weak base, pick up one of these protons, it doesn't matter which one. We take the 2 electrons of the carbon-hydrogen bond, kick them in to form a new pi bond, and the result is that we have our elimination product, there's our organic product, plus H3O+. So there is our E1 product, there is our SN1 product. And you see, the reason that these reactions are always in competition with each other is because they begin with an identical first step, the slow step, the rate-determining step, the formation of this high-energy carbocation. Once that happens, we can either have an SN1 pathway or an E1 pathway. What are the requirements for the E1 and SN1 reactions? Well, we have to have a good electrophile. That's a proper electrophilic substrate. And as we saw in the last example, tertiary substrates work well, and that's because the tertiary substrate will form a tertiary carbocation. This species right here is a tertiary carbocation, and we know that as far as carbocation stabilities go, tertiary carbocations are better than secondary, which in turn are better than either primary or methyl cations. And in fact, primary and methyl cations are so poor, you can just cross them off. You're not going to see those form in solution. And so when we say proper electrophilic substrate, really this has everything to do with carbocation stabilities. Carbocation stabilities could be discussed in exactly the same way. We also need a good leaving group. This is especially important for an SN1. It was already important for an SN2 reaction, but really important here because the first step, the slow step, involves spontaneous ionization of this leaving group. If this is not a good leaving group, you've got no chance to make this carbocation. So we've got to have a good electrophilic substrate, a good leaving group, and finally we've got to have a polar solvent. That's really key. In this first step, the slow step, the rate determining step, you're forming ions, a cation and an anion. A polar solvent will solvate these, which basically means that they'll stabilize these ions. If you're in a nonpolar solvent, that won't happen. The energetic requirements go even higher. In other words, you need more energy in a nonpolar solvent, so much so that the reaction becomes untenable. So we need a polar solvent for these E1 and SN1 reactions. Those are our three main requirements. Let's look at some examples. Here is a molecule, a ring compound, which we place in methanol, so that's going to be our solvent, and we're going to form 5 products here. 5. It's going to be a combination of SN1 and E1 products. So let's look at this one carefully. We suspect that this could very well be SN1 and E1 based upon the fact that I have a tertiary substrate, so the carbon attached to the leaving group is also bound to 1, 2, 3 other carbons. It's tertiary. I don't have a strong nucleophile, which would rule out an SN2, and it's a tertiary substrate anyway, so that also rules out an SN2. I don't have a strong base, which would rule out an E2. I do have a polar solvent. Now the reason I'm talking about SN2s and E2s here is because, remember, if you have a good SN2 or a good E2, it will always be very competitive and really dominate SN1 and E1 pathways. So again, a good SN2 or a good E2 will dominate SN1, E1, and that's because the SN2 and the E2 do not involve those high energy carbocations. It's a lower energy process, easier. So it's kind of a combination of, I'm looking for the right things that tell me that this could be SN1 and E1, but I'm also looking for the absence of the right things that tell me it could be SN2 and E2. In the absence of a strong nucleophile, the absence of a strong base, that's what I'm really talking about. Tertiary substrate, polar solvent, this is going to be SN1, E1. So what's going to happen? In the first step, we're going to have spontaneous ionization of our leaving group. Whoops. Once we ionize the leaving group, we're producing a carbocation, which is trigonal planar. I started to continue to draw the leaving group in there, and I continued to make this carbon tetrahedral. That's a mistake. I want to make sure that we show the carbocation as trigonal planar in the area of that positively charged carbon. Notice in this case that there are no resonance forms associated with this carbocation. We do have a pi bond over here, but it's not going to be involved in any resonance forms. We're not going to be able to delocalize this positive charge. It's too far away. We can only move pi electrons one bond at a time, and if I try to move that pi bond over there, that would give this carbon right here 5 bonds, which is impossible, and it doesn't delocalize that charge anyway. So there's no possibility for resonance forms here. It's just a tertiary carbocation. But I want to make an important point right now. We started out with a substrate that was 100% S. Because it was 100% S, it's optically active. Right away, in this first step, we've produced a carbocation which is trigonal planar, achiral. It's no longer optically active. We've already lost stereochemistry in this first step. Losing stereochemistry is an important part of the SN1-E1 reaction. It's not necessarily a desirable part, but it occurs, and we need to be aware of it. So we form this carbocation. Now, at this point, we've got to think either SN1 or E1. Let's look at the SN1 pathway first. So I'm going to redraw our carbocation. And in the SN1 pathway, our solvent, which is this methanol, can simply attack. And what I want you to notice is that it's going to be possible for this solvent to attack either from the front face or from the back face. That is, we're actually going to produce two different oxonium ions. If it attacks from the front face, then our methanol will be located as such, with the methyl group in the back. If the methanol attacks from the back, meaning the bottom, remember there's a p orbital coming in and out of the plane of this paper, and it has equal orbital density on both sides. So when I say it when it approaches from the top, that simply means it's approaching the top of the p orbital and bonding to that orbital in that direction. If it approaches from underneath the plane of the paper, it's attacking the bottom of that p orbital, ultimately creating a new bond like this, where the methyl group is now in front and my oxonium ion is in the back. So we get these two different oxonium ions in which there are two different configurations at these carbon atoms right here. Well, all that's left then is for methanol to come along. We'll use two different methanol molecules to show this. Methanol needs to come along, pick up an acidic proton, and that will give us our two SN1 products. We get two products because we've got two different configurations at these carbons. In other words, we just produced a pair of enantiomers. One of them, this one, is the S configuration, or has the S configuration, and this one has the R configuration. So we produce a pair of enantiomers, and that's two of our 5 products that we're going to form. And this is an important reaction because it does demonstrate that the SN1 and the E1 reactions will lose stereochemistry. We started with 100% S. Because we form an optically inactive carbocation as an intermediate, our products must be optically inactive, which means we formed a racemic mixture. Okay, now on to the E1. The other possibility is that this carbocation, which we have produced and redrawn, will react with our solvent, methanol, in a different way. The methanol can pull off an acidic proton, and it will always pull it off from an alpha carbon. So I want you to look carefully at this carbocation. That's the carbon that bears the charge. There's an alpha carbon here. There's a different alpha carbon there, we'll call it alpha prime, and there's an even different alpha carbon there, we'll call it alpha double prime. Alpha prime and alpha double prime are different because they are different locations or distances away from this pi bond. Now what can happen in this E1 elimination is that we simply pull off an acidic proton. I'll draw the hydrogens at the alpha carbon here, and I'll show you the aeroformalism for this one. Our methanol will come in, pull off an acidic proton, and we will produce the corresponding alkene. Had I chosen a proton at alpha prime, we would have produced this alkene. Make sure I don't forget that pi bond that was already in the ring. And had I chosen a proton that was at alpha double prime, then we would have produced this alkene. And these are all three different isomeric dienes, as it turns out. We'd form all three of these products. So these three dienes plus this pair of enantiomers that were associated with our SN1 reaction pathway, those are our 5 products. SN1 and E1, always in competition with each other. All right, to wrap this up, let's look at the following question. Which electrophilic substrates will react fastest in an SN1 or an E1 reaction? And it doesn't really matter whether we're talking SN1 or E1. We now appreciate that they're always in competition with each other. The slow step, the rate determining step, is the same for both of them. So we can ask this question in this way. Let's look at these 3 substrates here. This is a iodine leaving group, iodine leaving group, iodine leaving group. We know the leaving group is important in either an SN1 or an E1. It's all the same here, so that's a wash. This carbon attached to the leaving group is primary. It's attached to only one other carbon. This carbon is secondary. It's attached to 2 others. And this one is tertiary. This is going to be the best. The tertiary substrate, all other things being equal, is always going to be better than the secondary or the primary substrate. Let's go to B. Once again, the leaving groups are the same. We have bromides everywhere. So that's a wash. We have a primary substrate. We have here an sp2 carbon that's attached to our leaving group. We can't spontaneously ionize a leaving group off of an sp2 carbon. We need an sp3 or tetrahedral carbon for this reaction to work, so we can just cross that one off immediately. So it boils down to these 2. It looks like at first glance that they're both primary carbons, but actually this is not going to produce a primary carbocation. That one surely would, and primary carbocations are unacceptable, so we'll cross that one off. But this one would actually produce a resonance delocalized carbocation. Let me show you what I mean. If I spontaneously ionize this leaving group, what I'm going to get is this allylic cation. It's actually a resonance delocalized carbocation. I need 2 different resonance forms to show that the carbocation, or the carbon that bears the positive charge, is not a single carbon atom, but it's actually 2 carbon atoms. It's this one and this one, as shown by these 2 resonance forms. Resonance delocalized carbocations are even better than tertiary carbocations. This is a really good carbocation that we would form. And so this is going to be the fastest substrate, electrophilic substrate, for either an E1 or an SN1. In this case, it would have to be an SN1. We couldn't form easily a second alkene on this 3-carbon backbone, but it's still going to be the fastest. Okay, let's look at the next 3. They're all chlorides. One of them is tertiary, and it's located at a bridgehead carbon on a bridged bicyclic. One of them is tertiary, and it's located right there at that tertiary carbon of this tertiary butyl chloride, and one of them is secondary. Well, right away we can say that the secondary is going to be better than either of the 2 tertiaries. This one down here has really got serious problems. Above and beyond being tertiary, that bridgehead carbon cannot flatten out. So, oh my goodness, what am I saying here? I'm sorry. I was thinking SN2. Somehow my brain got on SN2, and I was saying that the secondary substrate would be better than the tertiaries. I apologize. Of course, since we're talking SN1 or E1, the tertiary substrates are going to be best. No question about that. And so the question now is, which tertiary substrate? Is it going to be the tertiary butyl bromide or the tertiary substrate in which the chlorine is at the bridgehead carbon? This one, as we've discussed in class, has got some serious problems. The bridgehead carbon cannot flatten out. So even though it's tertiary, we're not going to be able to form a trigonal planar, emphasis on planar here, carbocation. And that will mean that the carbocation will be much higher in energy than it would otherwise be. So We cannot form carbocations at bridgehead carbons of bridged bicyclics. We can cross that one off. Our best choice is going to be the tertiary butyl chloride. So, much like in the first case, tertiary substrate is best compared to secondary or primary. Here, the substrate which forms a resonance delocalized carbocation is better than anything else. Down here, of the two tertiary substrates, only one of them is acceptable. A tertiary substrate at a bridgehead carbon is never going to be acceptable. Last example, we've got six-membered ring compounds. Here we have an alcohol, an iodide, and an iodide. We know that the leaving group is important in an SN1 and an E1 reaction, and the OH group is a lousy leaving group. So we can just cross that one off. That's not going to work. Here we have two iodides. One of them is a tertiary substrate. That's a methyl group. This carbon that's attached to the leaving group is simultaneously attached to three other carbons. That makes it tertiary. This one is a secondary substrate. That's a hydrogen. So this carbon attached to the leaving group is attached to only two other carbons. The tertiary substrate wins out. So those are our examples of E1 reactions and identifying the fastest electrophilic substrate.